when we talk about position versus time graph, I'm going to bring some terms that you were familiar with or you should be familiar with since algebra class. Okay, so when we do position versus time, we will represent position in vertical axis. For those of you who are, math orientated, it's the y-axis, right? So position will always be the vertical axis. I don't like to use the y-axis because this vertical axis can represent many things. It can represent position, it can represent velocity, acceleration. It can represent many things. So it's just not y, right? So here, my vertical axis is known as the dependent variable, right? Dependent variable. Okay. Time in physics class most likely will be the horizontal axis. Okay. And time, or the horizontal axis, it is a independent variable. Independent variable. Okay? So, anytime when we see a graph of motion, most likely we will have time as the horizontal axis, okay? And vertical axis is going to be the position. Now, position can be represented as x if we were going x-axis only. It can be represented as y if it's going up and down, right? Or it can be represented as z if it's going through the page and out of the page. Or it could be r if it's an xy position, an xy plane, all right? So there are many different variables that can be used for position, okay? And time, of course, the horizontal axis is the independent. And position here is the dependent. All right? So, let's represent the position versus time graph, all right? And then the slope of that, it says, represents the velocity equation. Well, how does that come about? Well, let's take a look. If I were to draw here's the position represented by x, and here is time represented by t. All right? The position will have unit of meters, and time will have unit of seconds. And let's say I have a graph that represents position versus time. If I were to find the slope of this graph, right? To find the slope, you know it is the rise over run. So here is at t, let's call it t initial, right? T initial. Math, they would say t1, and then this would be t2. But I'm going to call that t initial, and I'm going to call this t final. And then at t initial, my position is x initial. And at t final, I'm going to call that position x final. The slope, right? The slope of this difference right here I guess this should be the purple one. And then this here is the rise, which is delta x, and that is the x final minus the x initial. That's the rise. And this here is the run, which is delta t, and that is the t final minus the t initial. And the slope is equal to basically the rise over run. Or simply delta x over delta t. That should look familiar to you. That is my velocity. So my velocity is equal to, right, the slope, which is delta x over delta t. And that is simply x final minus the x initial. Divide that by, right, t final minus the t initial. So that slope of position versus time is really representing the average velocity between the two time intervals. Okay? So the slope of the position versus time graph, right, represents the average velocity between the time interval. Okay? So, when, what is that? I don't know what that is, sorry. It's like an orange highlighter or crayon or something. So, the slope of the position versus time, if it's constant like this, that means it's traveling at a constant velocity. Because my slope between all the time intervals are exactly the same. Then it's moving at a constant velocity. When the slope is not the same between the time intervals, that means there's definitely change in velocity. And when there's change in velocity, there's definitely an acceleration. All right? So let's take a look at movement number one. For movement number one, it looks like when time is 0, my position is 0. So when I put Position is 0, my time is 0. All right, so when 1 second, my position is 1 second. 2 seconds, my position is 4 seconds. 3 seconds, my position is 9 meters. And 4 seconds, my position is 16 meters. 5 seconds, my position is 25 meters. So when I graph this thing, this does not look like a straight line. This looks like a parabola, like a disease. Ebola, parabola, right? So this parabola right here represents the motion of an object of position versus time graph, right? So this is movement 1, right? Well, if you look at movement 2, the movement 2, at 0 seconds, my position is 0. 1 second, my position is 5. 2 seconds, my position is 10 meters. 3 seconds, my position is 15 meters. 4 seconds, my position is 20 meters. 5 seconds, my position is 25 meters. So if I look at the slope between each time interval, right, it looks like 5 meters per second from 0 to 1 second, 5 meters per second from 0 to 2 seconds, no, 1 to 2 seconds, and 5 meters per second between 2 to 3 seconds, and so on, right? So in between is like 5 meters per second is the slope. 1 to 2 seconds, 5 meters per second. 2 to 3, 5 meters per second. 3 to 4, 5 meters per second. 4 to 5, 5 meters per second. So the average velocity between each time interval is constantly 5 meters per second. So it's moving at a constant velocity. All right? So the constant slope of movement 2, right? Okay? Therefore, the 3 dot means therefore. It is moving at a constant speed I could say velocity, right? Constant velocity of 5.0 meters per second x hat. Okay, positive 5 meters per second x hat. However, if I were to look at the slope value between 0 to 1 second for movement 1, that's my slope value. From 0 to 1 second, my slope value is actually just 1 meters per second. The slope value from 1 to 2 seconds is this, and that is 4 minus 1 over 1 is 3 meters per second. So my velocity between 1 to 2 seconds is greater than velocity 0 to 1 second. And similarly, if I were to look for the velocity between 2 to 3 seconds, which is that, this slope comes out to 9, right, minus 4, which is 5, divided by 3 minus 2, which is 1. So this is 5 meters per second for the slope value. And this will be 7 meters per second and 9 meters per second and so on if you continue to solve for the slope values between each time interval. Okay? So what does that mean? This means that movement 1 is definitely an accelerated motion. Right? This motion, right, represents an object moving, right, with increasing speed right, during every second. So you could tell it is moving, right, with increasing speed, right, by every second. Matter of fact, it's increasing by 2 meters per second every second. Average. Average. Okay? All right. So let's take a look at some position versus time graph and how we can interpret its motion by looking at just the graph itself. Okay? I'll post a video of this on Schoology. So here, if I were to look at a position versus time graph, okay? First thing I would do is always identify my time axis. So I would draw my time axis at 0 vertical. So here is my time axis. I would always define that and draw it in. Okay? So I know where my reference points are. And this time axis value will be in seconds. It says it right here. Okay. Now, if I were to ask someone to describe the motion of this object's complete trip, someone may say, well, Mr. Kim, it looks like it's going up a hill and then like sort of stay in the plateau region and then like it sort of like rolls down and then goes all the way down below the ground and then it sort of like crawls out of the ground again back to the ground level. And that would not be correct, actually. This motion is only happening horizontally only on the x-axis. All right? So if I were to sort of like draw out an x-axis, so here's my positive x and here's my negative x, right? And let's say here is my origin, 0. This motion, actually, I'm exaggerating this obviously, but it starts at 0. It doesn't always have to start there. It could start like at 100 or it could 250. It could start way down here, negative 100 or negative 50, right? It could start anywhere. But this particular graph started from 0. And then it actually moved to positive 200 meters in 10 seconds, right? Then it stayed here for 10 seconds. It didn't go anywhere. It stayed at 200 meters position for 10 seconds. Then it went backwards 50 meters in 5 seconds. They stood here, and then it didn't stay actually. And then it continued to go in the negative direction, past the origin, right, to 100 100 meters behind the origin. Then it turned around and came back to the original place. That's the motion of this. Okay? It started at the origin, it went 200 meters in 10 seconds and stayed there for another 10 seconds at 200 meters. Then it went back 50 meters in 5 seconds. Then it went back, right? 250 meters in the negative direction in 20 seconds. Then in 15 seconds, it came back towards the origin of 100 meters, like that. That's what happened. So it never went up and down the hill or below the ground and came out of the ground. Okay? So once we understand that, now I would like you to see if you can find the average velocity as time moves from A to B, B to C, and so on, C to D. I'm going to give you guys 4 minutes, 5 minutes to work on this, and we'll go over it together. All right, so let's take a look at finding the average velocity as the object moves from A to B. From A to B, it looks like my velocity, average velocity from A to B, is simply nothing more than position B minus position A, right? Divide by TB minus TA, right? Therefore, my position B is 200, right? So 200 minus 0 over TB, which is 10, right? Minus 0. So this is really nothing more than positive 20 meters per second, x hat, is what we have. I hope everybody got that. Then velocity from B to C, right, is equal to position C minus position B. Divide that by TC minus TB. And that is 200 minus 200 over 20 minus 10. And that is 0 meters per second x hat. So I didn't go anywhere. Well, at least I didn't change my position at all. From C to D, right, my velocity from C to D is equal to xd minus xc over TD minus TC. And that is, right, 150 minus 200, divide that by 25 minus 20. And that is negative 50 over 5. Therefore, it is negative 10 meters per second x hat. And then from A to E, right? A to E, all you have to do is just draw a line from A to E and then find the average velocity. And to do that, just find the slope of this blue line right here. So the average velocity, I should put the vector notations down. The average velocity from A to E is position E minus the position A over TE minus TA. And that is equal to negative 100 minus 0 over 45 minus 0. And that comes out to negative 2.2 meters per second x hat. So you just stick with the rule, and it doesn't make it hard. It's very easy. Okay? And then A to F. Well, A to F is just simply from position A to position F, and all I have to do is find the slope of that, and that looks pretty easy because that slope looks like 0, right? So maybe this should be from A to E, right? And then A to F, my velocity vector from A to F is xf minus xa, right, over tf minus ta, and that is 0 minus 0 over 60 minus 0, and that is 0 meters per second, etc. Let's just find the rest of these. Let's do the velocity from D to E, right? D to E. And then let's find the velocity from E to F, because we're going to need it later. Find these two. Let's go. I'll give you a minute. All right. So D to E, it is basically negative 100, right, minus positive 150 over 45 minus 25, and that is equal to, right, negative 250 over 50 over 20, and that is negative 12.5 meters per second, etc. And the average velocity from E to F, we have 0 minus negative 100 over 60 minus 45, and that is 100 over 15, and that comes out to positive 6.67 meters per second, etc. All right? Well, we can now actually graph velocity versus time graph using the same idea. So if we were to graph this position versus time and find the velocity between 0 and 1, right? And then 1 and 2. So this looks like 2 meters per second. This looks like 2 meters per second. This looks like 2 meters per second. So if I were to graph the slope values versus time here, the slope value from 1 to 2 seconds is 2. 0 to 1 second is 2. 1 to 2 seconds is 2. 2 to 3 seconds is 2. So it is just a constant slope value of 2 meters per second from 0 to 3 seconds. That is my velocity versus time function. And the area of this between the graph and the time axis represents the displacement. Which is basically the change in position. How do we get that? Well, here's the height, right? Which is 2 meters per second is the height, geometrically speaking. And here's the base, right? Which is 3 seconds, right? So area is equal to base times height, right? Well, base is 3 seconds, times height of 2 meters per second. Look, seconds cancel out, giving me 6 meters. And that's exactly how much it changed from 0 to 6 meters in 3 seconds. So, if we were to graph this previous graph here of this motion, we said the slope value for this was positive 20 meters per second. This was 0 meters per second. This here was negative 10 meters per second. And the d to e was negative 12.5 meters per second. And this e to f was 6.67 meters per second. So when I graph these slope values, this is exactly what it looks like. Positive 20 meters per second from 0 to 10 seconds. 0 for B to C. C to D, negative 10. D to E, negative 12.5. E to F, positive 6.67. Booyah. All right? So, what you need to do now is your homework will be pages 20, 21, 22. They go pretty fast. They're not that hard. And 23 and 24. They're not that hard. They're really easy. It should not take you more than 25 minutes. Or maybe 30 minutes. But that shouldn't be that hard. All right? Up to and including page 24. Any questions? All right. Thank you for joining me. Hopefully next class will be taught from school. All right. If you don't have any questions, have a wonderful day. Arrivederci. Ciao. All right. Thank you, Mr. Kim. Have a nice day. Thank you too.